Hi, I'm Dr. Incognito. In this video, we're going to have an introduction to implicit differentiation. Implicit differentiation is essentially the chain rule. So we'll start by reviewing the chain rule. The derivative of a composition, f of g of x, is equal to f prime of g of x times g prime of x. The derivative of the outside times the derivative of the inside. So implicit differentiation is basically the chain rule, but with an unspecified inside function. Now when you look at this formula, the inside function g and the outside function f are both unspecified. So in our applications of implicit differentiation, the inside function g of x will be unspecified, but the outside function f will be some specific function. As an example, if we want the derivative of g of x to the fourth power, then this is a composition where g of x is inside of the fourth power function. G of x is an unspecified function, and the function f is the fourth power. That's a specific function. And the derivative would be, according to the chain rule, the derivative of the outside would be 4 times g of x to the third. That's the power rule. And then times the derivative of the inside would simply be g prime of x. As another example of this, suppose we had the derivative of the sine of g of x. So in this case, g of x is an unspecified function, and the outside function is the sine function. That would be f in the chain rule. And so the derivative would be the cosine of g of x times g prime of x. F prime of g of x times g prime of x. Now one catch with implicit differentiation is that the unspecified function is usually written in the format of a single letter, which is not too unfamiliar. Oftentimes we write things like y equals f of x or u equals g of x. So oftentimes we give functions single letter names. So let me just write the chain rule with the unspecified inside function being called by a single letter. So let's say u is a function of x. In fact, let u equal g of x in the chain rule formula. Then the derivative of f of u, what does the chain rule formula look like in this format? If u is g of x, I just put a u right there. So it's going to be f prime of u times g prime of x. Well, g prime of x would be u prime in the single letter format. Just like f prime of x in this equation, f prime of x could be called y prime. In this equation, u equals g of x. G prime of x would be called u prime. Or u prime could also be du dx. So this is what the chain rule looks like in the single letter format, where u is taking the place of the inside function. So u is equal to g of x. F of u, where u is a function of x, the derivative is f prime of u times u prime. Let's look at an example. Suppose we want the derivative of u to the fourth, where, remember, u is a function of x. So if you look at this, it might not look like a composition. We have to remember that u is a function of x. And so this example is basically just like this example, using the letter u instead of g of x. So u is a function of x, so this is 4 times u to the third times u prime, or 4 times u to the third times du dx. U is a function of x, so u prime is du dx. This is implicit differentiation. U is implicitly a function of x. The derivative of u to the fourth is 4u cubed times the derivative of u. The chain rule. Suppose we want the derivative of e to the u, where u is a function of x. Then we use the chain rule. The derivative of the outside function, the exponential, is itself. So e to the u times u prime. And frequently in these examples, the single letter that's used for the function is actually y. So suppose that y is an unspecified function of x. Then what is the derivative of, say, y cubed? The derivative of y cubed with respect to x. So y here is an unspecified function of x, and therefore this is a composition. We have a function inside of a function. The inside is called y. It's unspecified, single letter representation for the function. And the outside function is the specific cube function. So we're going to use the chain rule. The derivative of the outside is the cube function. We know how to take the derivative of that using the power rule. So we're going to get 3y squared, and then times the derivative of the inside. The inside function is y. That's an unspecified function of x. Its derivative is y prime, or dy over dx, dy dx. So the derivative with respect to x of y cubed is 3y squared times y prime, or 3y squared times dy dx. Contrast that with simply the derivative with respect to x of x cubed. Here these letters match, and so this is just an ordinary power rule problem. This is not a composition. So the derivative is simply 3x squared. The derivative with respect to x of x cubed is not a composition, just regular power rule. The derivative with respect to x of y cubed is a composition because we're assuming that y is some unspecified function of x. Y is taking the place of g of x. Let's fiddle around with this a little bit more. What would be the derivative with respect to x of something like x squared times y cubed? X squared times y cubed. So here what we have is a product. X squared is a function of x, very straightforward. And y cubed is also a function of x, but in an implicit way. Because we're assuming that y is some function of x, so that y cubed then is a composition of y, which is a function of x, and the cube function. So first we're going to use the product rule. The derivative is x squared times the derivative of y cubed plus y cubed times the derivative of x squared. That's the product rule. First, x squared times the derivative of the second function, which is y cubed, plus the reverse, the second function times the derivative of the first function. And now for the derivatives, they look a lot alike. This one is the derivative of x squared. This one is the derivative of y cubed. Notice the difference. X, x, those match. This is an ordinary power rule. The derivative is 2x. So this is y cubed times 2x. Here, y, x, those letters don't match, so we have to ask ourselves, well, what is y? If y is independent of x, then we can treat this as a constant and say the derivative is 0. But in implicit differentiation, we're making the assumption that y is some unspecified function of x. If y is an unspecified function of x, then the derivative with respect to x requires the chain rule for y cubed, because the y is inside of the cube function. So we have 3y squared for the derivative of the outside, and then y prime for the derivative of the inside. The outside function is the cube function, its derivative 3y squared, and then the inside function is y, its derivative y prime. So this is the format that you see in a typical implicit differentiation problem. Let's try one more. What about the derivative with respect to x of the log of x squared plus y squared? Where y is a function of x. So first we have to use the chain rule because we have the log of an inside. So 1 over x squared plus y squared times the derivative with respect to x of x squared plus y squared. So this is 1 over x squared plus y squared times, and now the derivative of x squared plus y squared is the derivative of x squared, which is 2x, plus the derivative of y squared. The derivative of y squared is a little bit different than the derivative of x squared. The derivative of x squared is just an ordinary power rule, 2x. The derivative of y squared involves the power rule, but also the chain rule, because this is a composition. Y is an unspecified function of x, and therefore y squared is a composition. So we have to use the chain rule. 2y, that's the power rule for the derivative of the outside, times y prime, that's the derivative of the inside. So we get 2x plus 2y times y prime over x squared plus y squared. So there's a pretty complicated example of the derivative of an expression that involves an implicitly defined function of x. That would be y. Y is implicitly a function of x. Okay, so there's an introduction to implicit differentiation. Thank you for watching.